Welcome to my little presentation on some of my favourite physics toys. I've been thinking about putting this together for a while. Hope you enjoy it. The first one in no particular order are these amazing ice melting blocks. I should say at the end of the video there's a list of the costs and the locations you can get these from. These are essentially a piece of aluminium and a piece of MDF or something like that. They look basically the same, and what I would do is to walk around the class holding these and let the students touch them and get them to tell me which one they think the ice will melt on fastest. I'm going to put an ice cube on each of these. Now, of course, the aluminium will feel colder even though they are both at the same temperature, both at room temperature. And so if they go with that, they'll say, well, the one that feels warmer is the one that will melt on fastest. And they will form their hypothesis based on their observations. And then this is what actually happens. So there's supposed to be two of these rubber rings. I've lost one. But as you'll see, there isn't any need. So here's a thermal image of the two. You can see that they are both basically at the same temperature, about here on my scale. Here's me and my ice. And as soon as the ice goes on the aluminium, you can see it starts to melt. Whereas over here on the MDF, it is sitting unchanged, really. Here's a top view of the ice melting, and I would probably let it melt all the way before I then showed the students. So I won't delay you with that, but you can see that we're now 2.5 minutes in. And you can see the ice on the aluminium has melted more or less entirely, and the ice on the MDF has not. So I'm removing the ice here so that I can dry principally the aluminium plate, and then take a thermal image of the two again. I would go around the class and get them to touch these plates again, and they will notice that the aluminium plate is significantly cooler now. You can see it's down here at the bottom of the range, whereas this one really hasn't changed from where it was at the start. And you can see there's a little bit of cooling there, but very localized. And of course, there's all kinds of physics that we can explain with that. We have the reason that the aluminium plate feels cold to the touch, the reason that the aluminium plate feels colder because it is colder afterwards, and the energy conservation, where the energy to melt the ice is coming from the internal energy of the aluminium. So because the aluminium has lost internal energy, the average kinetic energy of the molecules has fallen, the temperature has fallen, and it feels colder because it is colder. It has lost energy, whereas the MDF does not feel any different because although there has been some localized loss where the ice cube was, if you're touching over here, nothing's changed. So I think it's a really good demonstration, and it can be explained at different levels, depending on the age of your class. The fire piston, this I would use at GCSE for the compression of gases. There have been GCSE questions, whilst they are not terribly detailed in terms of the physics behind this. There are GCSE questions that have been asked around what happens to a gas if you squeeze it. So what you have with the fire piston, if you're unfamiliar, is a thick plastic tube. You have a tight fitting plunger with an O-ring washer here. And as you'll see in a moment, There's a metal projection here with a little dimple in the middle. This is some gun cotton, which needs to be kept very dry, otherwise this won't work. But this I think is excellent. I use it at GCSE. Obviously I use it at A-level with thermodynamics, particularly with engineering physics when I'm teaching that. And this allows you to demonstrate what's going on inside a diesel engine. So here you have the parts, which I am trying to clearly show you on my video. The gun cotton goes into that little dimple on the metal projection. It's important that it doesn't project too much over the sides, because otherwise you'll drag it down off that little plinth when you put the tube on top, and it'll not work terribly well. One important point about this, it does need to be kept in good order, but when you squeeze it, you need to squeeze quickly and hold. And you can see there that with the very rapid and adiabatic compression of the gas inside, the air inside gets so hot that the gun cotton ignites. So that is the fire piston. Now this is the model that I have bought. I have used a different model where the tube was not removable. The problem with that is you have no means of getting out excess unburnt gun cotton other than hitting it really, really hard and making it ignite. I have had that problem on one occasion with a previous model. This one is better because you can take it apart and remove unburnt cotton if you're having trouble. If you put too much in, then you can find it doesn't ignite. So that's the fire piston. I really do like that. I think it's great. The merge cube, this is a relatively recent thing for me. You can buy these from Amazon, among other places. There are various pieces of software for your mobile or your tablet that you can use with these. Some of them you have to pay for. There are games. The one that I'm demonstrating here is the solar system, and I think this is really good. It's even got some sound effects. All right. So there's the sun. You can rotate the cube in your hand and you can see the planets. If you click on the eye, you get the information on the planet. As you rotate your hand, you get different views. You can pick different planets to investigate. And we have the Earth coming up, and we can see the International Space Station orbiting the Earth, which is quite nice. So I think this is really good. It's not terribly cheap for what it is, but I like it as a fun way for students to look at the solar system. And I imagine there will be further pieces of software. There is one for the body, but that, whilst the cost is modest, there is a cost to that. And as a physicist, I wasn't so interested in that. But I think that's really neat and very engaging on a fairly low academic level. The Mirroscope, which I've called Mirage, I like this. The demonstration isn't tremendously good on video, but the Mirroscope, if you're not familiar with it, has it's like a flying saucer. The inside of the two halves are mirrored and there's a hole in the top, and what happens is you form a 3D image of the object you place in the center of the bottom, which you can see here, but it is more pronounced when you look at it in real life. There's my image, which I will helpfully point to now. So it's quite striking. I have used this as a point of interest as students have walked into the room. They've come into the room and tried to pick up the pound that they can see floating above my mirroscope. And of course, when they can't, they're quite intrigued by that. So I like that quite a lot. This is a little demonstration, again using a thermal imaging camera, which if you don't have makes it a little more difficult, but you can see here I have an aerosol. I have cheated perhaps in that I have heated the aerosol. I put the aerosol into some warm water, but the aerosol is, the entire thing is warm here. So the aerosol is at about 27 degrees. And when I press the button, you can see that the gas, when it comes out, is substantially colder than the aerosol. And this is the corollary, if you like, to the adiabatic compression that we did earlier. This is adiabatic expansion. The gas doing work against atmospheric pressure, and so the average kinetic energy falls. It is colder. So I like that. One that perhaps is more difficult if you don't have the thermal imaging camera, but you can always use this as a demonstration of that. This is one of my all-time favourite pieces of kit. I bought this from the States. It's the only place I know you can buy this. The clever thing about it is the valve system that the inventor has produced. But this micro vacuum kit allows you to boil water at something like room temperature. It's not room temperature, it's probably bath temperature. But here's my equipment. The base and the top fit very closely together. You can see here the temperature is about 50 degrees. I've used a turkey thermometer for this. I'm doing this at home during lockdown, and I didn't have a thermometer. I'm not able to show you the temperature afterwards, but you will know that the temperature of the water after the procedure hasn't actually increased. It has probably fallen slightly, but I'm going to take some of this water, put it inside my micro vacuum chamber, and then I'm going to reduce the pressure inside the chamber. You do have to keep at this until you pretty much can't withdraw any more air, but when you do, you get satisfactory results. I tend to do this, and then having had the students stick their finger in the water before I put it into the chamber, I get them to stick their finger in the water that they have just seen boiling inside the chamber. The view is obscured, you have to look quite closely here because vapor forms, condensation rather, forms on the inside of the chamber, but you can just about begin to see the water boiling now, and you will see rather more, there we go, rather more pronounced boiling going on. So we put that water in there at 50 degrees and it is actually boiling now, which helps to dispel the idea that boiling only occurs at very high temperature, of course. Taking that off carefully to avoid rapid decompression and water going everywhere inside the chamber. So the water has been seen to boil, take it out, pass it around. I tried to show you the temperature, but the turkey thermometer needs to be more fully immersed to demonstrate the temperature, and that obviously wasn't going to work there. So I would take that out and pass it around so that the students can tell me that the water isn't any warmer than it was before. Many of them will say that it is, of course, which is an interesting test of just what your hands tell you and how accurate what your hands tell you is. But we could take the temperature and show that actually the temperature is a little bit lower now. By the time you've passed that around the class, the temperature will definitely be a bit lower, but certainly the temperature has not gone up. So they can all go home and they can tell their parents that you told them to stick their finger in water that you had just boiled, and what's worse, they did it. You can also use this for other things, of course. I don't have any marshmallows, but you could put a marshmallow in there, drop the pressure and see the marshmallow expand dramatically. And of course, sadly, when you increase the pressure again, allow it back to atmospheric pressure, the marshmallow collapses. Here I have one of those little press-on hook things, and as we know, they work by the difference in pressure on the inside and the outside of the device. So by dropping the pressure on the outside, then the sticky on device, the name of which I do not know, falls off, as you'll see. You can see I'm struggling here, I'm doing this on my own. I would normally get a student to hold the chamber so that when the pressure drops enough, it falls off very clearly for the rest of the class. But I don't have a class at home here, thankfully. So there it is. A clear indication of how they work, that by pushing it down, you're driving some air out from behind it. So there is a pressure differential between the two sides, which is enough to hold it on and allow it to support some weight as a hook. My final demonstration, I haven't done a video of this because it doesn't really work terribly well on video. But if you take, these are 50mm chromium steel ball bearings. I've chosen chromium steel because I believe they are harder than stainless steel. They're also much cheaper than stainless steel. This is about £20 worth here. And chromium steel doesn't rust the way stainless steel will if they get damp. And given that you're going to be holding these in your hands when you're doing the experiment, they are likely to rust. So the idea is to put a sheet of paper over one and then bang the other ball bearing into it really hard. This is an energy transfer, moving from kinetic to thermal energy store. You will actually smell the paper has burnt. If you use the right kind of paper, you may even get to see the singeing on the side, and you may also see a pressure wave immortalized in the paper when you do this. So I like this demonstration as a very direct energy transfer. I would do it as a demonstration, not as a class practical, largely I suppose for safety reasons, but also a class set of these is expensive. But I would certainly not let the students bang these ball bearings together themselves. Too much danger of fingers being caught, and with the amount of force involved, a lot of damage would be done. So there's my kit list. The microscale vacuum apparatus at this time, which is June 2020, is selling for $36 from Teacher Source. I paid import taxes and delivery charges on that too. The customs did not believe that this was for educational purposes, and therefore I was taxed on the import. The fire piston comes from Timstar, £27 at this time. Ball bearings, £8 each, plus delivery gets you up to about £10 each. The Mirage, or the Miroscope, is between £5 and £8. You could buy them in Tesco's at one time. I think you can buy them on Amazon. I have given you the Wish website here. The melting blocks from Rapid, £16. There may be other suppliers I don't know. And the Merge Cube, Amazon, £25. Again, there are other places you can buy that from, but I just wanted to give you an example of where to buy it from. And finally, I have this and other videos on YouTube. If you like what you see, you might like to look at what I'm doing for my students. This is my first video for teachers, but there are lots of others I've done for students. Some of them chemistry and biology, mostly physics, and quite a few at A level if that's of interest to you. Thank you for watching.